Hello, I am Colette Levens and I will be presenting on radiative transfer modeling, specifically an application in astronomy and astrophysics. First, I will introduce the premise of the project. Next, I will describe the observed data that I used to create my robust model of the infrared spectrum of the dust disk around the white dwarf G2938. Next, I will go into the model setup, first discussing how I created the black body of G2938, and then go into how to calculate the dust density. The final part of the model setup will go over the materials and sizes of the dust grains. And finally, I will discuss how I evaluate the accuracy of the models that I create. A white dwarf is the hot core of a star that is left after star death. The dust disks of white dwarfs have been discovered to consist of debris from planetesimals that had moved into a radius of about 100 white dwarf radii around the white dwarf, and gradually broke down over time, although in some situations the initial breakdown may not be gradual. This breakdown of material explains the gas disks around some white dwarfs, as well as the metal pollution in white dwarf atmospheres. Since the material that is broken down is made of asteroids and planets, we can learn more about the formation and ultimate state of planets through the dust disks of white dwarfs. Since 2005, there have been almost 40 observed dust disks that orbit white dwarfs. Dust disks are observed through infrared excess from dust emission. I am studying the white dwarf with the best recorded data of excess infrared emission, which is G2938. The white dwarf G2938 is unique as the white dwarf with the brightest dust disk. In my project, I'm using RADAM-C3D for dust continuum radiative transfer. RADAM-C3D takes two steps to create the model from the data that I have. First, I compute the dust temperature for the entire dust disk using the thermal Monte Carlo simulation, and then I make the SED data and the spectra for the model. Debs and Sigurdsson, 2002, discovered the process of planets in a system that have disrupted orbits from stellar mass loss. Properties of the dust disk can explain post-main sequence star fate, such as whether they used to be planets and other such objects. I used observed data of the dust disk of G2938 from 2014 for my SED data. The SED data, which are the black points, map the initial spike in flux density from the white dwarf itself, and Table 1 is this SED data. The two infrared spectra files from the Spitzer Space Telescope were observed in 2007. These IRS files, which are the blue points, map the following spikes in flux density displayed by the dust disk. These IRS data are especially useful for their clear display of the silicate features of the dust disk, seen at about 10 and 11 microns. Finally, the third IRS spectra file data, which is the purple dots, were observed in 2006 and maps the turn-up that marks the change between the infrared spectrum of the star to the infrared excess from the disk. This purple IRS data was key in determining how to adjust the model to account for the dip between the infrared data we see from the star and the infrared data we see from the disk. And all this data can be seen mapped in Figure 1. The first peak observed in the SED data from wavelengths about 0.1 to 2 microns trace the infrared emission from the star. The peaks after this initial jump are the infrared emission from the dust disk. The first of these bumps after the bump associated with the star is most likely from an optically thick continuum. There are prominent silicate features, noticeable, as I mentioned before, at about 10 microns and 11 microns, so there must also be optically thin emission. To accurately model the data, I first plotted a black body of the star. For my black body, I used the version of Planck's law seen in equation 1, where h is Planck's constant in units of ergs times seconds, nu, which is wavelength, is varied from 10 to the minus 5 to 10 to the minus 2.5 centimeters. C is the speed of light in units of centimeters per second, Kb is Boltzmann's constant in units of ergs per Kelvin, and T is the temperature of the star in units of Kelvin. To adjust for units so that the output is in millijanskis, I then had equation 2. Using equation 2 to map our wavelength points to Planck values gives us the plot seen in Figure 5 on the next slide. And here is the black body of the star, which is the green line. In equations 3 through 5, I calculate the necessary variables used in the final calculation of dust density in equation 6, an essential variable for the formulation of my models. For equations 3 through 6, I decided to use cylindrical coordinates, and I decided to use cylindrical coordinates simply to make the math easier so that there's less conversion between Cartesian and the values that we need. The grid setup in RadMC3D does not support cylindrical coordinates though, so I used spherical coordinates for the RadMC3D grid setup. Since the cylindrical coordinates used for calculations are separate from the radiative transfer model itself, there is no loss of accuracy. Figure 4 shows a plot of the dust disk of G2938 with the spherical coordinate r, theta, and phi grid setup. The x, y, and z axes are in units of cells. For example, the max of each axis is 100 cells. In this figure, I modeled the temperature of the largest dust grain size, where the orange in the center is the warmest dust, and the dark blue at the edges is the coldest. Since I'm modeling the largest dust grain size, the overall temperatures are going to be low, as we can see, since the smaller grains are exposed to more light from the white dwarf on the outside of the dust disk, and the larger grains are in the more optically thick sections of the dust disk, with much less exposure from the white dwarf. I used two different dust species to model the dust disk. The first of the dust species is amorphous silicates, which are commonly used to model the silicate features of dust disks. Second is forsterite, which I use to capture the small features in the data presented by crystalline olivines, and forsterite is a magnesium-rich olivine. I use both amorphous silicates and forsterite to ensure that I don't lose any particular features of the dust disk that couldn't be modeled without the use of both dust species. Additionally, I used amorphous silicates and forsterite to follow the example set by Zhu et al. 2018, which is the most recent model of the G2938's dust disk. I chose 30 different grain sizes from A-min, which is the minimum grain size, to A-max, the maximum grain size, that follow a power law with index alpha of -3.5 for the amorphous silicates and forsterite to account for the dust grain size distribution. Both species and all grain sizes follow the same spatial distribution. Assuming that each dust grain is not exactly the same, I had RadMC3D calculate the weight of each dust grain size. I used a Rivana computer cluster to run the Python scripts that make the models. Rivana allows the user to run multiple models at once. Running models in Python only makes one model at a time, and when my models take anywhere from 3 hours to 11 hours to run, one at a time is far too slow. Rivana uses job scripts to submit scripts to run all at the same time, significantly increasing my efficiency and productivity. As opposed to varying one parameter at a time, I varied several variables at once in a 9-dimensional grid and calculated the chi-squared values of each model to evaluate the fit of the model to the data. Increasing the inner radius of the dust disk, Rn, moves the first dip in flux density at about 2 microns lower and shifted slightly to the right. This makes sense, as increasing Rn means moving the inner radius of the disk farther away from the star, which would decrease the flux density of the dust at the inner edge, as well as shift the start of the dust disk to the right. Smaller grain sizes reach higher temperatures, which is why we can see the model shifting down between a smaller minimum grain size and a larger minimum grain size. When the minimum grain size is set at a smaller value, the dust is farther away from the white dwarf. When the minimum grain size is set at a larger value, the dust is closer to the white dwarf. The temperature of the dust is dependent on the model parameters that I input. This means that the dust temperature varies from model to model. Following the nature of dust disks, I allow each dust grain size to attain an independent temperature. This is especially useful to me as these independent temperatures ensure that the smaller grains in my models are hotter than the larger grains in my models. Figure 5 shows the current best model that I have made of the infrared spectrum of G2938's dust disk. I will use this model and other models of similar accuracy for modeling several other white dwarfs in the future. I will use CASIS, which is Combined Atlas of Sources with Spitzer IRS Spectra, to find data of the white dwarfs that have verified dust disks. My goal is to analyze the models that I will make to find statistical averages for values such as inner disk radius and scale height. I will identify patterns in parameter build that match infrared spectra data from most, if not all, of the white dwarfs. I also want to consider a large array of materials, and the properties of these materials will aid in identifying an age range for the dust disks as well as the white dwarfs themselves. These patterns have the potential to teach us about the formation and ultimate state of planets, which will not only further the field of astronomy, but also physical and statistical analysis. Thank you for your attention.